Hello. In this video, I'll be talking about electric potential and potential energy. We've already looked at the idea that if we've got two charged particles, there will be a force acting between them. Here, I've got two positive charges. If I imagine this one is fixed, I could move this one towards the other one by applying a force. I'd have to push it towards the other charge because it's being repelled by the electric force. So as I move this charge to the left, I am of course doing work. I'm applying a force over a distance. Now, if I was to let go, this would start to move away and it would gain kinetic energy. So clearly, as I do work moving this charge closer, I'm converting the work I do into potential energy stored within the system. Right. We've also seen the equation for the electric force, F equals K Q1 Q2 over R squared. The electric force extends to infinity. So if I was to take this charge away to infinity, off it goes, it's now an infinite distance away from this one, it would no longer be experiencing an electric force. There would be no electric potential energy when they're an infinite distance apart. As I bring it closer, I do work and potential energy is gained, which when I release it could then be converted into kinetic energy. Right, what I'm going to start off with though is looking at the electric potential. So if I just consider a point in space here, distance r from the centre of this charge, I could work out a quantity here, the electric potential, VE. The equation for this is the same constant, 1 over 4 pi epsilon naught, what I sometimes just call K, Q over R. So this would calculate the electric potential at this point in space due to this charge. There's a definition for this which is unbelievably important. This tells you the work required to bring a positive charge from infinity to this point in space per coulomb of charge. So I'll make up a number as an example. Let's just suppose you've plugged in all the different values and you've worked it out, and let's say it's 1000. Let's look at what it is. Work required, joules per coulomb. 1000 joules per coulomb. That tells you that if you have to bring a 1 coulomb charge from infinity and put it there, you'll have done 1000 joules of work. Let's do that. As I push this charge closer and closer and closer, I'm applying a bigger and bigger force over a distance to get there. I've brought it from infinity. I've done 1000 joules of work. Lovely jubbly. If I was to bring a 2 coulomb charge, positive 2 coulombs from infinity to this point in space, I'd have done 2000 joules of work. There'd be 1000 joules on each coulomb, and there's 2 of them. So that's what we mean by electric potential. How much work would be required to bring a positive 1 coulomb charge from infinity to that point in space? Now let's just think about this positive 2 coulombs again. I'm bringing it in from infinity and putting it there, and I would have done 2000 joules of work to do that. Well, now there must be 2000 joules of potential energy stored there. In exactly the same way, if you was to squash a spring by applying a force, then you would have elastic potential energy stored. I'm bringing these charges closer together. I'm storing potential energy. In this case, I've done 2000 joules of work, so there'd be 2000 joules of potential energy. So we could think of potential energy in a system as being VE, your potential, just multiplied by the charge that you move from infinity to that point in space. Not quite so keen on that. Let's think of it as work done rather than the potential energy. That would be the work done to bring this charge from infinity to that particular point in space. We could generalise that if we prefer. Who says you've got to bring it from infinity? Well, you could just put a delta VE in. If you're bringing from one point in space to another, say from here to here, you could just work out what is the potential difference, delta VE, multiplied by the charge you move from here to here, and you would get the work done. So let's just suppose the potential here is 800 joules per coulomb. If I move my 2 coulomb charge from here to here, it would require 200 joules of work per coulomb, and I've got 2 coulombs, so I'd have done 400 joules of work. If we do indeed consider moving from infinity, at infinity, the potential is 0. So coming from infinity, my potential difference to here would be the 1000 joules per coulomb, and we could think of the potential energy therefore as being 1 over 4 pi epsilon naught Q1 Q2 over R. That's your equation for potential energy when you've got 2 charges. That's your equation for potential. These are all to do with energy. They are scalars. So where we looked at, well, what if there's multiple charges when we're dealing with force and field? We can very similarly do the similar thing here. If I had one charge here, one charge there, and I'm asked what is the potential here, all we would do is this. How far away are we here? R1. How far from this one? R2. We've got the charge, we've got the distance. You work out one potential, VE1, at this point in space. You've got this charge, you know your distance. Work out VE2. And they're scalars, just add them together. You would just add them together. Don't need to do it as vectors, no direction, it's a scalar, just add them together. Okay. And then we could easily work out how much work is required to bring a charge from infinity to that point. You just multiply your potential by the charge and it will tell you the work done to bring it from infinity to that point. What if we've got a negative charge Well, a negative charge, let's imagine bringing a positive charge from infinity. I wouldn't need to push it, it would be dragged in by the electric force itself. I would actually have to do the work pushing it away to infinity. So if I consider a point in space here, VE does equal 1 over 4 pi epsilon naught Q over R. But here, this is going to give you a negative potential. Let's say, for example, minus 2,000 joules per coulomb. So I wouldn't have to do 2,000 joules of work to bring the charge from infinity to that point in space per coulomb. That's the work that the electric field would do. It would pull it in. This would accelerate in. It would gain kinetic energy on the way in. I would have to push it back to infinity. Now that this charge is here, the potential energy of this system, I'll go 1 coulomb multiplied by minus 2,000. The potential energy of this system here is minus 2,000 joules. Potential energy can be positive or negative. I think they're all of the main points on potential and potential energy, and of course there are some questions to have a go at.